Hello, I'm Carl. In this video, I'll be talking about permanent joints in the context of manufacturing assembly methods. During this module, we'll seek to differentiate different types of permanent joints, identify appropriate use of common permanent joining techniques, and evaluate design considerations for permanent joints. A mechanical joint is a section of a machine which is used to connect one or more mechanical parts. We classify joints as non-permanent or permanent. Many industrial machine joint types are non-permanent. That is, they are designed to be assembled with fasteners and to be easily separated or disassembled. Permanent joints, however, as the name implies, are designed to hold together forever. They're not easily separated without damaging parts. Examples include welding, brazing, soldering, adhesive bonding, and riveting. Welding is a method of fabricating a permanent joint. It is typically used to create joints in steel, aluminum, or some thermoplastics. In general, the process consists of using electrical current fed through an electrode to bring the base materials to their melting point and to stir the joint together while the electrode is consumed. As the joint cools, the two pieces of material are permanently joined and can only be disassembled by cutting them apart. The materials that are being joined should always be the same or very similar. For example, welding a piece of 6061 aluminum to a piece of 5052 aluminum is generally okay as the material compositions are similar. Welding aluminum to steel is not recommended as the two metals melt at very different temperatures and the resulting joint would be very brittle and not structurally sound. There's many resources available for determining the weldability of materials. Welding generally requires some amount of training and a lot of practice to become proficient. In certain industries, certifications are required in order to demonstrate the proper level of skill, for example, in pressure vessels, lifting bales, and aerospace applications. Welding shouldn't be confused with brazing or soldering, which don't melt the base metal when creating the joint. The three most commonly used processes in welding manufacturing are SMAW, shielded metal arc welding, commonly referred to as stick welding, GMAW, or gas metal arc welding, commonly referred to as MIG welding, GTAW, gas tungsten arc welding, commonly referred to as TIG welding. Examples of other less commonly used processes include spout welding, plasma arc welding, electron beam welding, and friction stir welding. Shielded metal arc welding, SMAW, is the simplest, least expensive, and most widely used arc welding process. It is often referred to as stick welding or manual metal arc welding. The filler metal is obtained from the electrode. Shielding is provided by decomposition of the electrode covering flux. The decomposition of flux creates its own atmosphere, which helps to control the welding process. All ferrous metals can be welded in all positions using SMAW. A welding voltage of about 15 to 45 volts and a welding current in the range of 10 to 500 amps is generally used to produce an arc with a temperature of about 5000 C. Average bead size is 3x the rod diameter and not to exceed 5 times the rod diameter. Slag covering the weld bead after the weld should be left in place until the weld cools. It helps to control the rate of cooling and can cause the weld to become brittle if removed too soon. Gas metal arc welding, GMAW or GMAW, is a high-speed, economical process that is sometimes referred to as metal inert gas welding or MIG welding. The electrode is bare, containing no coating or core. The shielding is to protect the molten metal from reacting with constituents of the atmosphere. It's supplied by an external gas, usually containing one of a mixture of the following gases: helium, argon, or carbon dioxide. Voltage is constant and amperage varies based on weld parameters such as material type, thickness, shielding type, wire alloy, and thickness. MIG welding is one of the easiest types of welding for beginners to learn. Gas tungsten arc welding is referred to as TIG welding. It utilizes a non-consumable tungsten electrode and separate filler metal in the form of a wire. Inert shielding gas is supplied through an annular nozzle around the tungsten electrode. The tungsten electrode serves only to maintain the arc. Shielding is obtained from a gas or gas mixture, usually helium, argon, or a combination of the two. TIG allows the operator greater control over the weld than other welding methods such as shielded metal arc welding and gas metal arc welding. TIG results in stronger, higher quality welds. However, TIG welding is difficult to master and somewhat slower than other welding techniques. There are several welding design considerations. Good joint design does not rely on the weld bead to hold the joint together. Consider slot and tab interfaces. The slot and the tab, when fitted together, provide a great deal of strength for the joint. The weld bead permanently joins the two components but does not provide added strength to the joint. The heat affected zone. Consider area around the joint affected by the heat of the weld, including thermal expansion, warping, residual stress, and cracks in some materials. Some example welding joint types are shown here. They include butt joint, corner joint, edge joint, lap joint, and T-joint. Weldment edge preparation includes a variety of groove types, including square, single bevel, double bevel, single and double V-groove, J-grooves, U-grooves, and flares. Joint surfaces must be prepared and be clean without any rust or foreign debris. Also, the electrical ground must be clean and bare metal. Brazing is a permanent metal joining process in which two or more metal items are joined together by melting and flowing a filler metal into the joint, with the filler metal having a lower melting point than the adjoining metal. Brazing is not generally used for structural joints. Brazing differs from welding in that it does not involve melting the workpiece. Brazing differs from soldering through the use of a higher temperature and much more closely fitted parts than with soldering. During the brazing process, the filler metal flows into the gap between the close-fitting parts by capillary action. The filler metal is brought slightly above its melting temperature while protected by a suitable atmosphere, usually a flux. It then flows over the base metal in a process known as wetting and is then cooled to join the workpieces together. A major advantage of brazing is the ability to join the same or different metals with considerable strength. Techniques include torch brazing, which is most common, furnace brazing, and induction brazing. Brazing often uses dissimilar materials that are joined together. For example, in heat exchangers, where a copper tube might be brazed to a stainless steel fitting. Often it's used with non-ferrous materials. In induction brazing, usually ferrous materials are heated with the electromagnetic field created by alternating current and an induction coil, which has the advantage of being very repeatable. Soldering is a process of joining two metal surfaces together using a filler metal called solder. The soldering process involves heating the surfaces to be joined and melting the solder, which is then allowed to cool and solidify, creating a strong and durable joint. Soldering is commonly used in the electronics industry for the manufacture and repair of printed circuit boards and other electronic components. Soldering is also used in plumbing and metalwork, as in the manufacture of jewelry and other decorative items. Adhesive bonding is one of the simplest joining techniques where materials are permanently joined together by an adhesive substance, such as glue or silicone or epoxy. An example of a modern adhesive application is automotive frame joining, pictured here, where adhesives replace traditional welding techniques. This application highlights the advantage of adhesives for complex joint geometries requiring high bond strength. Adhesive joint application factors include environmental and thermal conditions, loading modes such as shear, tension, compression, bending, or torsion, materials, joint shape, fit tolerance, and life cycle dynamics. Factors for the adhesive joining process include surface conditions, oil tolerance, substrate material, contamination, temperature, humidity, clamping force, and cure time. Appropriate adhesives must be selected for each application. Due to the wide variety of design considerations, there's no one-size-fits-all adhesive for all purposes. 3M, Saint-Gobain, and Henkel are leaders in the adhesives industry. 3M's design guide is a useful learning resource. Rivets are a type of permanent joint commonly used in airplanes, boats, trailers, and engineered structures. A solid rivet is a cylindrical shaft with a crowned, round head and a tail end that is hammered or crimped with a compression tool. The protruding tail end is deformed, holding the joint assembly together. In airplanes, rivets are common because their strength is well known and the holes do not alter the temper of the metal skin. Though considered a permanent joint, rivets can be destructively removed by drilling them out. A disadvantage to riveting joints is that most solid rivets require access to both sides of the joint. However, blind rivets, aka pop rivets, are a type of rivet that requires access to only one side of a joint. A solid riveting tool includes pneumatic and hydraulic hammers and bucking bars. Blind rivets use a pop rivet tool and pulls a pin through the rivet. Rivet materials, geometry, and installation are governed by ISO and ASME standards. This concludes our discussion of permanent joints in manufacturing assembly methods. After completing this module, we can differentiate different types of permanent joints, identify appropriate use of common and permanent joint techniques, and evaluate design considerations for permanent joints.